Let's talk about equivalent resistance. The idea is you have a combination of resistors that you want to replace with a single resistor. And at the same time, you want the battery to continue to perform the same. That is, you want it to put out the same current. There should be no change in the behavior of your battery or power source when you replace these multiple resistors with a single resistor. That's the idea with equivalent resistance. And what I want to do is, you may have already seen the formulas, but I want to derive the formulas because I think you'll have a better idea of what equivalent resistance is if you see how it comes about. So we're going to start with the series case. And I've got my battery here. I've got my two resistors connected in series. I know they're connected in series because I've got a path between them that has no junction. That means any charge that passes through R1 has to pass through R2. So that's what it means for these to be connected in series. And as a consequence, they're going to have the same current passing through them. So I am going to draw my current. I'm going to assume my current is going this way. And now I'm going to set up my loop rule. I'm going to trace clockwise around my loop. When I do that, I get positive V0 minus V1 minus V2 equals 0. Okay, so now let's apply Ohm's law to both V1 and V2, because those are the voltage drops across the resistors. So this would be I times R1 minus I times R2. Again, they're the same current for both because they're connected in series. And I'm just going to move that to the other side so I can just put an equal sign there. Okay, now what I need to do is evaluate what the circuit looks like when I have the equivalent resistor in place. So that is going to look like this. Let me draw my circuit diagram. This would be REQ. And this is my battery here, V0. And it's putting out, it has to put out the same current. That's the idea with REQ. Yes, I've replaced these two resistors with a single resistor, but the current is unchanged. When I set up the loop rule for this situation, it's just going to be V0 minus VEQ. I'm still tracing clockwise here. Throw in Ohm's law for VEQ, and that becomes IREQ. And I'll just move it to the other side, so that becomes an equals. And hopefully you can see, just by comparing, these equations are the exact same if REQ equals R1 plus R2. So that's the condition for REQ. If REQ is the sum of the resistors in series, then everything works. And so we've got our rule. The general rule for connecting, for the equivalent resistance for resistors in series is just this. That's the general rule. And in this case, of course, I would just add together my 7 ohms and my 6 ohms. 7 plus, actually, let me do that over here. Do it under here. This is 7 plus 6 for R1 and R2, and of course, that just equals 13 ohms. So that's the series case. Now let's go to the parallel case. Here I've got two resistors connected in parallel. I know they are connected in parallel because a charge comes out and it has to choose a path. Here it comes to a junction. It's either going to go up here through R2 or here across R1. It can't do both. These are mutually exclusive paths. So it's the paths that are actually connected in parallel. And since I have one resistor on each path, those two resistors are connected in parallel. So what I want to do is draw my currents. So I'm going to have current coming this way. I'll call that I0. And then at this junction, the current splits. I'm going to have I1 and I'm going to have I2. So I can write down my junction rule. I naught equals I1 plus I2. Okay, now let's do the loop rule. I'm going to start with the lower loop. I'm going to go clockwise. So for the lower loop, that's going to be V naught minus V1 equals 0. Use Ohm's law, and I'm going to get V naught minus I1 R1. And so, of course, that's just going to be equal to each other. Now I'm going to do the outer loop. That's going to be V naught minus V2. And when I do that, use Ohm's law, that becomes just I2 R2. Okay, in both of these cases, I'm going to go ahead and solve for I1, or excuse me, solve for the currents. So solving for I1, that's V naught over R1 equals I1. And over here, that's V naught over R2 equals I2. Now what I need to do is look at my circuit with the equivalent resistance. So I'm replacing those two with a single resistor, as I did before. And I get a circuit that looks identical to what I drew up above. The key thing is, once again, this current here, this current is the same as over here. It's I naught. It's the current coming out of the battery. That cannot change. That's the crux of what it means to be an equivalent resistance. The battery behaves the same. It puts out the same current. So when I do the loop rule for this, it's just V naught minus VEQ equals 0. And so that just becomes V naught equal to I naught times REQ. And we can solve for I naught. That's just V naught over REQ equals I naught. Okay, so I solved for these currents. Now I'm going to take them all and plug them back into my loop rule. And if I do that, I'm going to have V naught over REQ equals V naught over R1 plus V naught over R2. And hopefully you see that the V naughts are all going to cancel. And so what I'm left with, these all cancel, is just 1 over REQ. 1 over R1 plus 1 over R2. And remember that in general, the general rule for resistors connected in parallel is that we often refer to this as the reciprocal rule. 1 over REQ equals the sum of these reciprocals. Okay, so this is the general rule right here. For this case, when I just had two resistors connected in parallel, it worked out to this. And if I do it for my actual values, okay, then I'm going to have 1 over 7 plus 1 over 6. Okay. So if I do this, I'm going to run out of room here, so let me move down here and rewrite that. 1 over REQ equals 1 over 7 plus 1 over 6. Okay. Now you could, of course, plug this into your calculator. I'm just going to go ahead and get the common denominator and do it that way. So the common denominator is 7 times 6, 42. Okay, so I got to multiply this first fraction by 6 on both top and bottom. So 6 over 42, and this one by 7, so 7 over 42. So that's 13/42. Okay, so this is the key step. Whether you do common denominator like I did, or if you just plug 1/7 plus 1/6 in your calculator and get the decimal. It doesn't matter. You come to this step here. Okay, this is not the answer. To get the answer, you have to take the reciprocal of both sides. The reciprocal of the left side is just REQ. The reciprocal of the right side is 42/13, which is approximately equal to 3.231 ohms. So that would be the answer. One last thing I want to point out, notice that in the parallel case, the equivalent resistance was less than each of the two resistors. 3.231 is less than 7 and of course is less than 6. That's what happens with parallel resistance. The overall resistance decreases. And in the series case, if I go back up to the series case, my overall resistance was 13 ohms, which of course is greater. When you connect them in series, you increase the overall resistance.